let's now look at an example of a transonic centrifugal compressor. So generally it's found in transonic compressors, even though secondary flows can be present, shock losses will be the dominant source of loss. And so in fact, the type of loading that you specify has to control the shock losses. So the first example that we'll cover here is a 4.5 to 1 pressure ratio compressor for a heavy duty diesel application. And obviously at these high pressure ratios, it's very important to look at the mechanical aspects of the design as well. And so we'll briefly talk about these as well during this presentation. So the Transonic Impeller here is a heavy duty diesel engine turbocharger application. It's a 4.5 to 1 pressure ratio, 98 mm diameter impeller. And this was actually a collaboration with Cummins Turbo. And what was interesting about this impeller was that in fact, no one had been able to improve the performance of the impeller for more than 10 years. And originally the aim was to achieve a straight filament design with better efficiency and similar stress levels as this impeller. And then this type of loading was used that generally tends to be better when you have strong shocks. So by using an aft-loaded distribution on the shroud, you actually help to reduce the loading on the inducer. And then as a result, you reduce the strength of the shock. And then using this type of loading resulted in this impeller just within a week. And it was, as you can see, a 3-dimensional impeller as opposed to the straight filament baseline design. And then what we are seeing here is a comparison of the flow field between the two designs. And you can see the strong shock in the inducer of the conventional baseline here. And you can see the strength of the shock is reduced in the inverse design. And also the complex interaction of the shock and the tip clearance vortex can be seen here. And in fact, the tip clearance vortex itself is reduced in the inverse design. And the combination of these two, in fact, can be achieved through the specified blade loading. And this plot is also very useful because you can clearly see the reduction in the strength of the shock. So this is the blade loading at 95% span. And the red line is the conventional and the green line is the inverse design. And you can clearly see the reduction in the shock strength in the inducer, which was very strong in the conventional design. So some detailed stress analysis was also done because the resulting impeller was 3-dimensional. And upon the stress analysis, it was found that the maximum stress was quite similar between the conventional and the inverse impeller. Just the location of the maximum stress was different. So in the original impeller, it was happening somewhere near the hub, whereas here it's happening kind of in the middle of the blade. But in terms of reliability, there was actually no difference between these two impellers. And then what you see here is the test data. What this plot shows you is the improvements in efficiency between the inverse design and the baseline as measured in the test facility over the map. And as we can see, over a large part of the map, we are actually getting 2.5 to 3% points improvement in the efficiency of this impeller. So now the second case that we're going to see is a much higher pressure ratio impeller. And this is also quite a well-known case. It's the SRV2 impeller that's been subject to very detailed LDV measurements at DLR in Germany. And in fact, it's also been subject to a redesign study, which was published in 2007. And that was a collaboration between DLR, MAN Turbo, and ABB Turbo. And they actually looked at this impeller and they tried to improve its performance by making changes to the meridional shape and blade angles. And they did about 24 different geometries. And at the end of this work, what they found is that they can improve the performance by about 2 points at 100% speed. But actually the performance at other speeds, such as 90-80% speeds, was in fact less than the baseline SRV2. So I'll first share some CFD validation results with you, because obviously with these very high pressure ratio compressors, doing a proper CFD calculation is also very important. And so the LDV measurements here were used that were supplied by DLR to validate the CFD calculations. So initially, let's look at a comparison. So what you see here on the left are the LDV images. And obviously you are missing a small region near the end walls because of reflections. But otherwise, there's quite a quite a good match with the LDV measurements. And that's actually at this section here. So just before the trailing edge. And then at the trailing edge plane, again, we are getting quite a good match with the LDV measurements. And then this gave us confidence that we can actually use the CFD results to compare the performance of the redesign with the baseline. And then in terms of blade loading, we essentially started with a very similar loading to what we used for the Cummins case. And the difference was that in this case, as you know, with these very high tip speed impellers, in order to have a wide choke margin and to match the choke margin of the baseline, you need to have a certain throat area. And so the initial loading was with 0 incidence at the leading edge, but it was found that the throat area was too small. So in fact, by using the throat information from inverse design, adjustments were made to leading edge loading until the throat area of SRV2 was matched. And then this was confirmed by the CFD computations. And in this way, this type of loading was arrived at. So essentially aft-loaded at the hub with a very high incidence at the hub and the midspan, and also generally aft-loaded at the shroud, but again with very large leading edge incidence. And this then showed that the right level of choke margin was obtained. And then you can see a comparison of the 3-dimensional geometries. And on the left, you have the baseline SRV2 impeller, and you can see that it's clearly a straight filament design. And you can see the actual inverse design impeller over here. And again, some FEA analysis comparisons were performed between the baseline and the inverse design. And what you see here is the results of the von Mises equivalent stress on the main blade pressure and suction surfaces. And the material, obviously, with this high-speed impeller is this titanium alloy. And generally, it was found that the maximum level of stress was similar to the baseline SRV2 impeller, but of course, the distribution was different. And then this shows you the result on the splitter blades. And again, even though the maximum stress on the splitter is higher on the inverse design compared to the original, but actually the level of this maximum stress is much lower than the maximum allowable stress. So we are still within the safe margin for this impeller. And what's interesting is when you look at the modal analysis, so you can see here, in fact, there are significant improvements in the first, second, third, and the fourth modes. And so there are significant advantages in terms of vibration response of this 3-dimensional impeller. And here you can see a comparison of the CFD predictions between the baseline SRV2 and the inverse design. And you can see in terms of the efficiency, we are gaining between 2.5 to 3 percentage points across the whole operating range. So not just at 100% speed, but also at part load conditions. And this is very important if, for example, this were a turbocharger compressor for a diesel or a marine application. And then if you look at the detailed flow field, the lower image is the conventional and the upper is the inverse. And first of all, we can see that there is a strong normal shock at 50% span, which is then reduced to more of a bow shock with reduced Mach number levels for the inverse impeller. And also at 90% span, you can actually see a reduction in the shock strength and also a reduction in this low momentum fluid that seems to have accumulated in the blade passage. Then looking at the exit flow from the impeller, at the top you have this original SRV2, and here you have the inverse design. And you can see quite significant improvements in the exit flow non-uniformity in the impeller. And so the reduction in shock strength and the more uniform exit flow are the two main reasons for the improvement in the impeller efficiency. So some concluding remarks on transonic impellers. So basically, by applying 3D inverse design, it's very easy to control shock strength in the inducer. And generally, we find that using aft-loaded distribution at the hub and the shroud gives you very good control over the shock strength. And then a key benefit of using inverse method is that you automatically get the optimum pitchwise location of the splitter blades across the span. And this helps you to get a better matching onto the splitter, and that also helps with the performance improvement. In terms of stresses, for example, we saw in the Cummins case, we seem to have optimum performance with the straight filament design. And the only way you can actually get significant improvements is by looking at 3D impeller designs. And what we see, in fact, is that there are no significant penalties in terms of centrifugal stress for the 3D design compared to the straight filament design, as long as the 3D design is done carefully to minimize the lean angles at the leading edge. And also, we get significant improvement in impeller stiffness and vibration response, which is, of course, an added benefit.